Be assured that recording has started after hearing it like 10 times. Okay, so at some point I remember that a couple of you were asking me how can we do more complicated time steppings, and is it possible to do those ones? So I will present a simplified version of Rangakuta by just separating the diffusion coefficient. So for those of you who are not familiar with Rangakuta methods, I don't know if this is large enough, but if you had an equation where you had derivative of a time derivative of a variable as a function was given to you, then in order to integrate for one time step and march this variable y for one time step, you could calculate these intermediate variables that you can treat them as vectors. And then the total time stepping would be something like this. So we would have to follow this equation. And these k's are basically coming from, they have to be sequentially calculated based on the previous value and the previous case that you calculate. So this is just a reminder for those who may not be familiar with Rangakuta methods, but I think most of you are familiar with this. So I'm going to start, like always, with I'm not changing the model that we are dealing with. We are still going to deal with the Fitsunaguma one, but the same principles would still apply. You can use them. If you do a git pull, I've added a bunch of codes here, and I will, just in case that other people want to follow later on with videos, I will keep the raw versions here, and then I will just update the class codes at the end so that other people can follow. There is a single version, a single file version, and the multiple file version. I will just open the multiple file version, but it's nothing but if you want to know, we have repeated this several times, that it's just replacing this shader commands with the content of these files, init.frag, click.frag, and march.frag. And since we are going to concentrate on the time marching, we are going to work with the march.frag. So maybe make it smaller. I think we don't need to split it today. Okay. And I can concentrate on the march.frag. For those of you who are working with the single file version, all you have to do is you have to pay attention to this March script section. That content is basically here. The only difference is that I will be able to have some code highlighting here. Right, so this was the time marching scheme that we previously had. We would calculate the Laplacian, which was the Laplacian of the u variable, and then the derivative of u with respect to time would be some diffusion plus some reaction terms. That would be a function of u and v, and then derivative of v with respect to time would be just a function of u and v. So we were doing previously Euler time stepping, and we want to replace this Euler time stepping with the Rangakuta version. So in order to do that, I need to be able to do calculations of these k variables, intermediate k variables, and then I need to be able to update both of these ones. So by the way, if we had multiple state variables, you can treat this y as a vector of unknowns. So, and these k's become like vectors as well. So, and the derivative becomes a derivative vector, basically. So, in order to make my life a little bit easier, I can write a recipe that I pass basically the y variable, and based on that y variable, because this particular example that we have is not a function of time, we can just pass the y variable, and based on the y variable, we can calculate the k's. I want to design a function that gets the k variables. So let's say we want to get k's. And since we have variables u and v, we want to have two outputs. So I start with a void function that gets a float of variables u and v. And I need one additional thing, as you notice. Derivative of u is a function of diffusion. And the diffusion is basically the culprit that doesn't allow us most of the time to integrate the gates easily. And in order to do that, because most of the time when we are having problems, is that the gates are behaving or misbehaving in a certain way. In order to resolve those misbehavior, sometimes we can have a better time stepping. And the diffusion is not the one that is causing us problems. So we can assume that during this entire process of calculating K1 to K4, diffusion is a constant. So I can have a diffusion that I pass here, diffusion. And I want to return a K value for U and a K value for V. This will be the function that I'm going to deal with. So if I pass the U and V, these are the inputs. I can have these bunch of outputs, KU and KVs, that I can calculate at each time step. So KUs and KVs are nothing but the derivative with respect to time of U and V. I can actually start stealing from this Euler time stepping that we had. So KU would be diffusion. Instead of this lowercase u, I pass the dummy variable u. And for the v, I just pass the dummy variable v. KV, I can have this guy copied and pasted here. And again, I replace u and v by their dummy variables that are passed to this function so that I can update them, and then I can return from this function. The return for void function is not compulsory, but you can place it there. So this will be the function to calculate RK coefficients. Okay. So the first thing that I need to check is that I didn't introduce any bugs. Now, time stepping is like this. I need to calculate K1, K2, and K3, and K4. Right now, we were doing Euler time stepping. So if I were to run, I would get this solution. So I disable the Euler time stepping. So I get rid of this part that I want to replace. This was doing my time stepping. Now if I,
Hi, Abazar.
yes, I should be in the
Um,
class code.
I'm not sure if this is intentional, but did you mean to use for the A and B um, variables are defined in the preprocessor as lowercase u and lowercase v, um, and
This is
yeah, so I was just
intentional
wondering if
because lowercase
okay.
v and that's a good question. The lowercase u and lowercase v are the macros that read the color R and color the R channel of the color and the green channel of the color. So I want to separate that and I want to pass these ones as dummy variables to the function. Okay, so that's why I place them as capital U and capital V.
Ah,
Does
okay.
that make sense?
Yeah.
If you change any of these ones to, if you change it to U, you will get an error because this line by the preprocessor will be replaced by color.r and then you can't define a function. So you can't write color.r here as the dummy variable, you get an error. So we need to be careful about that. Does that make sense?
Yeah, that does. I just wanted to make sure it was correct.
Yep. I intentionally separated these ones to capital letters to make sure that we don't end up with some intentional, some um, unintentional changes. So as you can see right now, the code, if I start running, I have removed the time stepping, so nothing happens. Time is marching, but no, no waves are getting propagated or anything. Now the next step is to do our case, and we need to calculate our case. So what I want to do is I want to do my Rangakuta updates here. And for getting the Rangakuta updates, I need some case for the U variable and some case for the V variable. I will have float KU1, KU2, KU3, and KU4. And I need to have the same thing for the V variables. Case for the V's. And now we need to do the updates. So the first one is very simple. K1 is just passing the current variables that we have. So get K's of U, V. Now these are passed to the dummy variables and are replacing the dummy variables. Fusion. And then the outputs would be KU1 and KU2 will be calculated. So we get the K1s, KV1, sorry. Careful what you type in here. And then for the next step, I need to add half of DTK1 to KU1 to U. So if I just copy that one to U, I have to add half of DT times KU1. And to V, I have to add half of DT times KV1. And this will produce KU2 and KV2. And then similarly, from the next step would be also very simple, that these ones will change to 2's. You notice here, you have to add K2's to get K3's. And then the last step, get a full DT, so it's no longer half of that, K3's, V3, K4, and V4 will be calculated as outputs. So this gets all of our K's for our updates, and then we can update our U's. So my U will be previous U plus delta T times KU1 plus 2 times KU2 plus 2 times, this is, right now we are at this line, 2 times KU3 and plus KU4, everything divided by 6. So we had a dt, h is the delta t that we had, so it would be dt divided by 6. And then similarly, we can update v based on that. So all the u's change to v. So the ours, let's see. So now we have a RK4 Timesteping that we are updating u and v based on the RK4 scheme by just assuming that the diffusion coefficient during the Rangakuta updates, the diffusion remains constant during the Rangakuta updates. Now, we can make this one a little bit more fancy if you want. So there are for this particular scenario that we dealt with, we only have 2 variables, and instead of having multiple k's like so, you could have a secondary function like this that you had. Maybe I treat this one as a different code. So let me save this. So this was calculating K1, calculating K2s, K3s, K4s. And this was the final update. So we can do it a little bit differently as well. So we have the class code. Let me I can do a second version. Second version is right now identical to the first version. We go to the marching part. Instead of doing it like this, I could change this function to something that returns just a case for me, so that I can use them easily. And instead of receiving the variables like this, I could receive them as vectors as well, so that I can be closer to this formulation that we had here, because I said that all the y's could be treated as vectors. I just write this function get k that gets vector 2 types of UVs, and then a float variable of diffusion, and instead of returning nothing, it actually returns a vector 2 type variable. And first one, I want to return exactly the same thing that I was returning over there as the first component of the vector. And the second component of the vector, I want to be this. Now, I can again use the concept of macros so that I don't have to rewrite this one. I can say that whenever you see capital U, treat it as uv.r, and whenever you see capital V, treat it as, say, x and y. These are not really colors, they're components of a vector. It doesn't matter, both of them works. I can get rid of this part now that we had. Now the difference is that now we can work with vectors, and that's a little bit more concise, and I can comment out all of these parts. Instead of all of those ones, my k's now become vector two types, k1, k2, k3, and k4. I can define a vector uv that is a vector 2, u and v. That makes my life a little bit easier. And then for k1, I can say it's get k of, I don't know if the fonts are large enough. K1 gets UV and diffusion and returns K1, get K. For K2, UV, I have to add half of PT times K1 and then diffusion. For K3, I have to add half of K2. For K4, I have to add a full K3 here. Now, this section of the portion can be written as the derivative of u, right? So this is the change in u and v. So I can say that the derivative or the change in u and v is delta t times k1 plus k2 plus 2 times k2, sorry, plus 2 times k3 plus k4 divided by 6. And u can be updated by adding the change in u to the previous value, and v can be added by v uv and I. Now this is the vector implementation of the same thing that makes the implementation much more similar to what we had in here. It's much more closer to the original formulation or the mathematical formulation. Let's see if I didn't mess up anything. It should work. This is another implementation of the same Rangakuta 4. Remove these parts. So I would say this sort of formulation is much more similar to the mathematics compared to this formulation that we had initially. But the reason that I introduced the best method was for you to understand that right now we have only two state variables, but if we had multiple state variables, if we had like, I don't know, 30 state variables, and we wanted to update them using some of them using something and some of them using something else. The point is that the way to do it would be to use those output keywords to get the multiple Ks out of it, for example, for the Rangicutis. So yeah, that's basically what I wanted to talk about this session, because in all of the portions of the class we have been dealing with just simple Euler updates. I wanted you to know that you can do more complex updates. Now, if you wanted to also vary the diffusion, then you would need to write these Ks into textures out of the output. There is no other way to go around it, meaning you had to have multiple solvers, that each one of them is in charge of calculating one of these Ks. And then you had to have a last solver that blends all of these Ks together to calculate the final results. I would say that you at least needed to calculate K1 in a separate solver, K2 in a separate solver, K3 in a separate solver, and the last step when K4 was calculated can be the last step. So you would need at least 4 solvers to do a single time update, because the only variable that you can update at this point is your own particular point. You can't update the neighbors, and you can't know what happened to the neighbors in this time step unless you calculate it yourself. So the simplest way for that would be to have multiple solvers, basically, to deal with that. But I would say that in my experience, at least for cardiac problems, the diffusion is not the problem that you are dealing with, is one of the gates that is causing the problem. So the fancy steps can be applied to the individual gate rather than be applied to the diffusion. Right. Do you have any questions or concerns? No? Are you still there?
Yep.
Okay.
Yeah, I really appreciate it. I'll probably have to think more about what you just said about the different solvers for the cases where you're doing that. But no, I understood everything that you said up till now. It's very good. Thank you.
You're welcome. Okay.
Abuzar, so because you are not updating this diffusion for each of the sub-steps, it's not quite RK4, is it?
It's not really a full RK4 since you're not using it for the for everything. But as you know, for example, when you're using Rush-Larsen for the gates, you're not using it for the diffusion. So it's not a full Rush-Larsen when you are using Rush-Larsen for each.
Yeah. So could you just leave out the diffusion part and then just add it back in at the end?
You can also do that. So that's another method that you can do. That is commonly referred to as operator splitting, and you can split the diffusion from the reaction term. Just take care of the reaction term in whatever method or way that you want, and then take care of the diffusion term at the end. You can also do the diffusion completely first and assume that V is already updated with the diffusion, and then update the gates using whatever variable, whatever technique or method you want. Sometimes changing the order helps to stabilize the solutions.
Okay, yeah.
All right. So there are not any more questions. We can switch to Neil and see how he managed to solve the problem of the ghosting on the surfaces.
Okay, thanks, Sabajar. So let me just sort of remind people what we had and what I was trying to accomplish. So let's see. Hopefully you can see my screen and
Yep.
see, and of course this little thing is in the way. Okay. All right. So this is what we had before, and you may remember sort of one of the problems we had was that there was this kind of this weird thing that was happening on the top of the box, and also there were some strange things going on the sides. You can sort of see some weird things going on over there, and then if you look at it from different directions, it's not completely consistent. So that's one of the things I wanted to fix, and the other thing had to do with the transparency of the wavefront. There's something sort of strange about what the wavefronts themselves look like. So those are sort of two things I wanted to try to improve on, and then let me just sort of show you, skip to what it looks like now. This isn't quite the latest version. The latest version is in pieces, and I guess I need to put it back together. But anyway, okay, so this is the new version. Excuse me, I put a new ion channel model in this. This one has a tendency to break up, and so that's kind of the thing that we're interested in. And so notice that the improvements are that there aren't any strange goes on the top anymore, and then the waves themselves I think are a little more consistent. One thing I improved on here was I made it so you could change the transparencies of the waves. So like this alpha correction here, the alpha basically talks about how opaque each of the pixels that make up the waves, or the voxels that make up the waves, how opaque they are. So when alpha is equal to 0.1, as it is here, then each voxel lets 9/10 of the light going through it from behind come out through the front, and it contributes 1/10 of its own color to the light that's going through it. So for example, if I change this to something like 0.5, okay, then the waves are much more opaque. You can't see the filaments through them anymore. And by the way, another improvement I make, well, this is actually not an improvement. I think Abajar has filaments in his code also. But yeah, now the filaments are opaque, and the opposite direction is if I just change this to 0, okay, then the waves completely disappear, and you can just see the filaments themselves. Okay, and again, back to having it be mostly transparent, you can see the filaments through the waves. But to me, that's kind of a nice feature. You can sort of see the waves and the filaments at the same time. You can see the rotation around the waves around the filaments. Okay, so let me talk a little bit about
can you hear me, Niels?
I was doing. Yep, sir.
Oh yeah, sorry. I think I wish I had some of that, but also here you have this blue color on the inside. Maybe better would have just no color inside. Maybe white inside and the blue outside, so it doesn't interfere with the color that you see the transparent.
So you want the box? You want the box?
Yeah, it's transparent, but it's not transparent enough to see. I mean, I still not see clearly even when it's this transparent at 0.05, you cannot really see the vortex filaments that good.
So you're talking about this dark color, or are you talking about this?
Yeah,
this
no,
color?
that one. The background you have nothing. Yeah, no, the blue, the color you put on the inside the box to define that there's a
so
box.
this color.
Yeah.
Yes, this color is easy to change.
Yeah, I was just saying it's just maybe if the blue is everywhere outside and just whatever is the box is white, maybe better. I don't know, but I don't know. It's just something, just a minor thing.
Okay, yeah, that's actually pretty easy to change. So
yeah, sure. Mm-hmm.
Yep. Okay, so let me sort of go through through what was involved in making these changes. Let's see if I can get this to work. Okay, so hopefully you can see my iPad here. And so the critical feature had to do with the way that data was stored for the to produce all the data that's being used to color the wavefronts. And as Abhijit talked about when he was discussing this, the way the data are stored in this simulation is that you basically have a two-dimensional. Think of this as being two-dimensional. I'll use this instead. You have a two-dimensional array, but then in order to store three-dimensional data, you split the two-dimensional array into these individual boxes, and then each box is one slice out of the cube, right? So if you're slicing in the z direction, then each one of these boxes contains all the data for a particular value z. So you have like x and y, all the x, y values for a particular value z stored in this box, and then all the x, y data for another value z stored in the next box. Okay, so the way the data were arranged previously was that the data for a particular value z went all the way to the four edges of this box. So the problem was that the data that were stored, for example, on this line was in common to both of these two z-planes. So both this z-plane and this z-plane had data like along this line in common, and then also you have data for this z-plane and this z-plane in common along this line. Okay, so what I did was I took advantage of the fact that really the only data that we're interested in is data between the bottom of this value of x and this value of x, and we're not really interested in what's happening out there. So all I needed to do really was to instead of translating the data so that for a given value of x you cover this entire length from here to here, you just go from here to here, and then the same thing in the y direction. Okay, and then there was a similar kind of problem going on in the between z-planes, so that if you think about your z-planes as being arranged like this in the box, where the z-plane corresponding to z equals 0 is on the bottom, and z-plane corresponding to the total number of planes minus 1 on the top, then really the only information we're interested is in between these z-planes. So what that means is that you're not interested in data which is sitting up here. So in a lot of places the number to divide by is there's a minus 1 here instead of the actual mx times my. So those are basically the two changes I needed to make in order to remove the ghosts. So Abhijit, I only did it sort of in the places that I needed to for my simulation, and then you might want to do these kinds of changes in other places, places that I didn't modify. Okay, so let me also talk a little bit about how I did the transparency or opaqueness of the wavefronts. So I'm not sure what the official method is for doing this, like when you're doing games and stuff like that. But this is sort of the method that kind of made sense to me. That if this is the cube in which your simulation is running, then what you'd like to do is if here's your observation point, and then you're looking, for example, along this line, then what you should see is you should see this color here at the very back of the box. But then, of course, that this has to propagate through the entire cube to get to the front, and each voxel that it travels through has a certain opaqueness associated with it. So not all of this color makes it through the first voxel, and then of that amount of light, only a certain amount makes it through the next voxel, and then the next one, and then the next one, and the next one, until the light comes out the front. And then then as this light is traveling through along this ray, you also have the various voxels contributing their own colors. So, like for example, this red voxel here tries to transmit light along the ray, but not all the light gets through the voxel in front of it, and then of that light, not all of it gets through the voxel in front of that one. So to me, the algorithm that kind of made sense is this one, that whatever, suppose you have a voxel here that's, for example, red, and you have light being transmitted from behind, then you would say that like if alpha is equal to 0.1, then 90%, so 1 minus 0.1, 90% of the light from behind this voxel makes it through the voxel and appears on the other side. And then 10% of the light coming from this voxel contributes new light, and now this combination here, so the sum of these two quantities is the amount of light which emerges from this voxel. So the algorithm starts by deciding how much, what color is coming from the voxel on the very back of the box, and then this process is iterated as the light travels from the back of the box through the front of the box. So those were sort of the two improvements I made. So any comments about those two improvements? Do you think that was the right thing, or do you think I'm like way off base?
No. This is another method of looking at the problem. So your light source right now is at the back, and my lighting technique was to think as the areas that need to be illuminated are exist, and the lighting is coming from the front. So you shine something through it, and the areas that light reaches them start glowing, and then they contribute from the front to the back. I think the major problem that was there, I think that was the -1 that you added somewhere in the code that removed the ghosting. I think that's the major thing that we needed to have. Or there is something technically in the library or in the method that I'm using, the lines that you think that they are shared, they are not supposed to be shared unless there is some sort of interpolation happening between the pixels. So I am not assuming that there is anything shared between these ones. So I have to look through it, but there is a bug if it's assuming that there are these lines are shared, and then by removing those lines completely, you have basically hidden the bug, if that makes sense. But it points me to the direction that I need to go to fix it for a general case.
Right.
This is another example of lighting, which is very interesting, and I think good too. Thank you for taking the time to go through it.
Great. So to try to respond a little bit to what you just said. So if your original coordinates for example, the x direction, so this thing which you call texture coordinate, so this quantity originally runs from 0 to 1. And then of course what you want to do is you want to map this quantity which runs from 0 to 1 inside one of these boxes. So what you did originally was you took these quantities which run from 0 to 1 and you divided them by mx. Okay, and since there are mx of these cells in the x direction. So if you take this quantity which originally varies from 0 to 1 and you divide it by mx, then it will vary between here, from this location here and this location here. Okay, so what I did instead of dividing by mx, I put this additional factor in here, which is nx minus 1 divided by nx. And the result of that is now instead of mapping the quantities between 0 and 1 to this region, now it maps from here to here. Which is kind of natural anyway, because this is the same way, this is the same grid that you're dividing this XY plane into anyway. Okay, now you've got this little buffer region in here, so there's no overlap. And I think this is kind of the natural way to do it anyway. I'm not sure what the official method is. Like for example, if you were modeling a periodic system, a system which was periodic in the x direction, then you really would want to go all the way out to this line, because then the left side of the system identifies with the right side of the system. But if you're talking about a cube by itself, where the top and bottom or the left and right faces are not the same, then then I think this seems like it should be the natural method.
So to respond back to you, so your assumption is that we should have coordinates that land on the lines, right? But the point is that
yes.
the texture coordinate x for each of these pixels lands at the center of the pixel in this data structure. So it is never on the lines. always on the center of the pixel.
Oh yeah, I guess that would be another way of doing it. Then this entire box here would be shifted like half a cell,
Yeah.
half a tiny cell in each of these two directions. Yeah, so that
So
would be
when we
another
are
way of
reading
doing
the data, we are reading always at the center of the cell if you want to, and all the library is set so that it's reading at the center of the cell.
that.
So I
I
have
mean, you
to.
are doing interpolation though. You're doing interpolation, so
So
that
what
you're
I'm
actually
doing is I'm doing interpolation in the z directions and interpolations in the x directions when the marching x and y is passed. So maybe that's the part that is just shifting some of these ones to the other one. So
Yeah, so like when you're doing the ray casting, then in general the ray could travel through like any portion, it could travel through any part of this, not necessarily in the center of a cell or not necessarily on the nodes.
yes, yes,
So that's why you need to. That's why it really does have to be, since the values could be pulled from anywhere inside of this square, then you really do have to be careful, because like if you were to go all the way to the edges, then you would be interpolating from this line into this box right here, and then you get mixture of what's happening like in the next box with what's happening in this box.
yeah.
Okay, and of course I could show you where this appears in the code. I'm not sure if that's how interesting that is to people. So this is where I did most of the stuff occurs in this your VRC2F shader, so here's where I'm dividing. Instead of just dividing by mx, I'm dividing by like nx minus 1 over nx, and then that whole quantity is divided by nx. So I'm basically doing those kinds of things here, and then you can see when I'm dealing with the z slices, I'm dividing by this quantity also. Okay, and then the other interesting part of this is where I'm doing the ray casting. So again, the ray casting goes from the back to the front, the way I think about it. So that means that you want to start off initially with the first coordinate of the ray being at the back of the cell instead of the front. So I change this from front coordinate to back coordinate, and then the ray itself is now oriented so that it's pointing from the back to the front. Okay, and then I divide it up as so keep it divided up just the way you did. Okay, and then down here is where I'm accumulating the color from one as I'm going from the back to the front. I'm basically taking the value of alpha, taking 1 minus that quantity times what's already coming from the back, and then adding like alpha times the current voxel color. And then to address Flavio's point, all I have to do in order to change that the light blue color of the back of the cell is just change all of these to 1s. Okay, so it's just as trivial as that. Just change all those to 1s, and now the back of the cell back of this cube is white, and then it should work out fine. I just changed these. One of the reasons I changed this was to give it a little bit of, so I could actually see where the cube was, and the other was, frankly, so I didn't accidentally start modifying Abijar's code, and then I just have 2 different modified versions of the same code. I'm very prone to that.
Yeah.
That's also why I changed the colors of the wavefronts and things like that, so I wouldn't confuse the two models. Okay, so I guess I should mention also the way I'm doing filaments is to let's see, where did I put the filament part of it? I thought it should be in here. Maybe this part does. Maybe this one doesn't have filaments in it. Because I'm actually showing you code from like the actual code that I was showing you didn't have a make file associated with it, so I just modified things directly into abu.js. But yeah, actually the way I'm doing the filaments, I actually have to follow dudt as another variable. So I choose the alpha channel to model dudt, and then if dudt is smaller in absolute value than a certain number, then I consider that the wavefront to be stationary there, and then I have some arbitrary value for the actual value of u on the wavefront. And so when u is between 2 numbers, I'm sort of in the middle of the wavefront, and then dudt is basically stationary, then I plot a green line, a green voxel, which has no transparency at all. And then so that instead of plotting the color associated with the wavefront, Okay, so that's basically all I wanted to say. Not sure if anybody has any questions about what I did.
That was really good.
Yeah, it's very nice, Niels. So, what model, you say you put a new model there? What model did you put there?
Oh yeah, so I'm using Echebarrier Karma two-variable model because I needed a lot of breakup. So in fact, let me just sort of show you that part of it too, just for fun and excitement. Let's see. Okay, so this quantity RE here is the variable. This is a parameter in the model itself, and if I make it larger than 1, then the code goes nuts. So it produces a lot more breakup. You can sort of see the number of filaments starts to multiply very rapidly. Okay, so one thing that's cool is, as Abujar has already showed you, is that you have the ability to change the parameters of the model on the fly. So you can sort of see what happens, you can sort of see what the behavior is for different values of variables on the model. So if I change this back to something pretty small, then the filaments will gradually disappear because they're no longer subject to breakup.
So that's very nice. The other question is, do you see any difference in time of calculating the vertex filaments with your method or
Are you asking whether it slows down the code?
Huh?
Are you asking whether it's slowing down the code?
Yeah, you see any one is better than the other one in speed, or they're about the same?
I guess I chose this one because it seemed to do the best job of representing the filaments. If I try to instead choose, U and V between, narrow ranges, it just doesn't, just from a practical point of view, it doesn't seem to show the filaments as cleanly as this method. So of all the different methods there are of tracking filaments, this one so far has to me been the best.
Okay. It's still fast enough. Still doesn't.
Yeah, it doesn't seem to slow the code down really at all. All I'm doing is just taking the alpha channel and putting DUDT in it, and then I just do conditions on it to decide whether or not to plot an opaque green voxel, where the filament is.
I also saw that the first example you did, you have the stimulation at the surface. So have you been able to now study a little bit more faster the effect of the defibrillation by the surface?
Yeah, so I actually have another version of the code, which is kind of in pieces right now, where I've added more parameters to the control panel here, and I can vary, like when the stimulus is applied, how long the stimulus is, how strong the stimulus is, things like that. So Brianna and I have been, or actually Jenny and I have been looking at that a little bit to try to sort of see what how effective the stimulus method is. This code has sort of a strange problem in that you have to apply a really huge stimulus in order to detach the filaments, and that wasn't true for the Barkley model. So I'm not sure why there's this difference. That's another thing we're investigating.
Yes, so I'll tell you later on more when we did it with the 3-variable model. Also, it was a different dynamics too.
Sorry, which model?
With the 3-variable model.